Hello, everyone. It's a great honor to be back on the stage at Code Blue, and with the growing popularity of the AI applications. This year, we have focused on our research on leveraging attention for semantic detection. We aim to apply those features to address the challenges of detecting obfuscated and packaged malware that the blue team commonly encounter in practice. And we are TX1 Networks. We are TX1 Pre-Cert and Research Team. I'm Mars, a current research manager at TX1. And over the past years, I have the opportunity to speak at more than 14 cybersecurity international conferences. And my colleague Sheng-Hao, he is a team leader of our research team. And Ian is one of our dedicated researchers. And we will present the exciting content of this event here. And due to the time constraints, our agenda today will be very tight, but we have a very awesome content we share with you here. And first, we will maximize the challenges blue team's members face when dealing with the large volume of malware samples. And next, we will discuss how we use a practical neural-symbolic transformer we proposed to address this issue. And after providing a clear understanding of our proposed QIDA, our model, we will share how it has effectively assisted in a real-world scenario. And finally, we will present how those tools we can utilize by blue team at large. So, what is the difficult problem the blue team is currently facing? The sheer volume of the highly obfuscated malware samples and commercial large packets make it challenging to analyze and identify specific malicious behaviors. And additionally, Windows shellcode is often hidden and difficult to prevent. It is usually too late by the time the dynamic execution of shellcode is detected. And also, it is challenging. Experienced malware analysts can still decipher obfuscated functions by leveraging their accumulated knowledge over time. For example, using the tool IDA-Pro, experts can identify that the file flag belongs to the create file function. And they can then determine that the v13 is a file handle, a subsequent verify it against the invalid handle value before the proceeding to the get file size. The process of reasoning and reverse engineering program the code through the continuous data reference relationships is a methodology outlined in the UNIT's 2022 study. And however, the number of human experts is inherently limited. When faced with a larger volume of malware, the layer cannot scale to handle the work effectively. That is why we want to automate the process using AI modeling to ensure timely and precise analysis on a large scale. And in order to take the issue of identifying unknown API codes, we proposed a related method at Red Hat USA 2022. And our approach uses intent analysis as a foundation for performing semantic analysis of APIs and employ various expert rules to effectively identify the unknown API sequence. However, the method has its limitations. It requires human experts to write numerous rules to identify unknown APIs. And the sheer volume of a rule needed is overwhelming. And it is challenging to cover the entire scope comprehensively due to the human constraints and the potential for oversigning. So you may be curious about how human experts can determine unknown symbol from data relationships. Let's take a look at a few practical examples here. Consider a scripted Windows API with 7 parameters. Initiatively, among the various options, the only Windows API with 7 parameters is create file, and making it relatively straightforward to identify in this case. But what if the current unknown API has 4 parameters, and all possible options also have 4 parameters? In this scenario, it is essential to base our judgment on the parameter value and their data type. So for instance, if the first parameter is one of the type int, and the fourth parameter is a flag, with a common value like 105, 401, and 180, we can determine that the only resolve window among the amount of APIs is having this usage pattern. Our goal is to enable AI to learn and recognize such APIs through those detailed parameter characteristics and the usage habits. And now that we have already built up our code, and let's take an initiative look at our practical neural-symbolic transformer. We named our model CUDA with a standard for CUDA Cheng inference decompiler engine. Through our research in 2022, we utilized 10 analysis to identify unknown API by considering the function agreement precisions and tokenized symbol required for pre-operation. After proceeding through the trained model, we can calculate and obtain the possible API names. And the output is then applied to our 3 tools, designed specifically for the blue team's practical analysis needs, and is having proven to be helpful for the real-world applications. And of course, we examined the various past papers in our research. For instance, NDSS 2018 analyzed unknown API identification through static analysis methods, achieving quite high accuracy. However, the hidden Markov model, they use later precision-wise semantics. This limitation can create an issue when making association between different unknown APIs. So following this method, research at Israel had considered the similar issues, and they attempted to infer symbol names from data reference relationships and use attention mechanism to effectively recode position-wise semantic, resulting in higher end performance. But why is precision information so important? Significantly, it's close to related to the importance of semantic, and we apply precision-wise semantic encoding in our model. Because scaled dot product attention can effectively capture not only the numerical distribution typically found in API parameters data, but also the different semantics that each API's precision should inhabit through the precision encoding in attention. It can relate the data more accurately, and the semantics are projected into the 3-dimensional matrix of QK query key and value, can effectively predict the likelihood of each unknown API. And this approach allows us to comprehensively analyze the contextual and positional information, leading to more accurate identification of unknown API. And therefore, returning to the core idea, we aim to use a human aspect to analyze and understanding the behavioral intention associated with a unique attack method or API usage combinations. By combining the 10 analysis with AI models, we seek to model and automate the aforementioned human understanding process. And this approach allowed us to leverage similar data reference relationship encountered in the future to automatically inform attack behavior that resemble those observed during the model training stage. And among that, the relationship between different API can be analyzed through embedding and taint analysis. And the attention model is then used to recode the data usage habits or those common APIs. And here, we have introduced our CUDA architecture and the principle behind that. And now I will hand over to Sheng-Hao, who will share the case of practical application of our model.
Okay. So thanks for Master briefly intros about the idea of our transformer. However, we know that it's difficult for the directly to use the transformer on strip binary for the analyzing the low small way. So I will go more follow more to talk about how we use the word embedding NLP technique to capture the semantics of the strip binary and on the learning API sequence. So first question is how do we extract the argument value from the API codes without execute the binary, right? About this, in the Black Hat 2022, we have shared the idea to build up a practical symbolic engine to collect such argument value from any binary. For example, on the right side, you can see that is a result from the IDAPRO decompile result, and there is a magic number like 40042400100, which means on the decompile result, our Python engine only need to do is collect such a integer number as the list API code, so we can collect all the possible integer number used by an API code, and also we can replace the return value of any API codes with a magic number. So what if any further API code try to use a magic number from a previous magic number? We can make sure we can understand and make sure the relationship between the previous API code and the further API codes. Okay, but however, we know if we want to directly use the NLP, the word embedding method, to capture all the possible semantics of every integer number in a binary, that is insense. Why? Because as we know, in the Windows 64-bit, the integer number can be large, very large, to about 128 terabyte, which means if you want to create a very, very large database to collect all the vectorized semantics of each integer number, you should have at least a very large, around 100 terabyte database. That is too large. So, which means if we want to solve such a question, this challenge, we have to find some way to reduce the size of the lookup table. So we consider from the reversing engineering perspective. So as a human expert, seeing that is an unknown API code right here, so as a human expert, we might guessing, is that is integers right there? Is that a memory patch? If the answer is yes, so the human expert will double check, is that data type is a Unicode string or ANSI string, local buffer, or data structure? So we can classify such an integer number into human readable string, like its data type, like Unicode string, ANSI string, their data type as the token ID. And also you can see another case, right, like the integer number C000, that is a memory page and executable. So human expert might guessing is that a shell code or assembly script on this memory page. So we can classify such an integer number into a human readable string, like the token will be assembly script or a shell code script. Okay, but however, as we know, in the reversing engineering, there is still a lot of integer number. They are not memory page, but carrying with the meaningful semantics. You might say, what? Why? What could it happen? Because actually, Microsoft have predefined a lot of magic number that is just pure numerical magic number, but carrying with the semantics. For example, your Windows kernel receiving integer number like A0001, and the Windows kernel will say that is definitely is a H-key current user. And another case, like you have a blue screen, BSOD, and you can see the Windows kernel will receive a C000FD, this error code, and Windows kernel will say maybe somewhere, somehow, some program just happened, segment fault, stack overflow happening. So which means each Microsoft actually have predefined a lot of magic number into human readable string. All we need to do is identify such a magic number predefined by the Microsoft, and we can classify such an integer number into Microsoft predefined string. Okay, so once we can create a practical symbolic engine to extract all the argument value of the triple binary, and also using the NLP method to tokenize the semantics of each API codes, so we can try to create a symbolic engine in AI. And we would like to share our pre-trained model directly used for the community, directly to use on the GitHub clone. And we want to share a AI model has been pre-trained, and everyone just use it. This AI model can directly to identify any unique attack behavior. So we try to choose a data set that is as small as possible, very any kind of real attack case can be coverage into this data set. So finally, we choose all the APT group binary listed on the MITRE. And because we believe only national APT attack groups will have the best quality of their binary, because as we know, national attack groups, they don't want their binary exposed to the AI detection, EDR detection. So they should have the best quality of their code. So we choose them as our data set. And finally, we using the CUDA to pre-train about AI model about 26 hours, and we get a very tiny version of the AI model, and we try to use it on the real world. And let's see an unusual case right here. We choose from the vast total. And this sample, you can see this binary is highly obfuscated with the inclusion algorithm. And this binary is very difficult for the traditional Yara rule matching, pattern matching. But our AI engine can detect, oh, that is internet open A right there because of the argument value. The argument value is 0, 1, 0, 0, 0. This argument value is the usage of such a argument value is very unique, only happen on the internet open A, and the magic number 1 put at position 2, the argument stand for the magic number internet open type direct. And another case on the right side, you can see here, that is A0002, that is a magic number stand for the HKey current user. If this magic number put at position 1 will be stand for HKey current user, and only Regis key relate Windows API will use such magic number. So our AI model can detect this API maybe that is a Regis create key X right here. Okay, but although our AI model is very powerful and very tiny, easy to use, but we are pretty interested about we are very curious about how do it's so powerful and easy to use. We try to know how under the hood, how does our AI model do the inference, the progress, how it works. And about this, we using the Facebook Meta's platform Captain in 2023 to explain the progress of AI model to do the inference. And you can see here, that is an unknown code, that is a backdoor with highly obfuscated behavior right here, try to using the Regis query key value X, this Windows API. And you can see, because our AI model will try to know which API it try to use, this backdoor try to use, but it don't have the symbol names, right? So it have to try to guess. And how do it guess? First, our AI model can check the first argument value is A002, so that is definitely HKey current user. So our AI engine will say, maybe I should choose some Windows API related to the Windows Regis key. And finally, it found out the second position put a Unicode string, put at the argument value position 2. So finally, it only choose those Windows API related to the Windows key, like Regis open key X, Regis set value X, or Regis query value X, such a Windows API. Okay, so we just share the idea how we train the AI model used for the detection on the malware data set we choose from the VirusAuto. But actually, we are more than curious about, is there any APT groups they actually use such a very sneaky hidden API code to hide their suspicious behavior for a long year. We didn't know them because of we cannot use such an AI detection. But now we have such a weapon to again them. So can we capture them? So to answer this question, we use the VSTotal to search all the obfuscated binary and only have vendor consider and detect them as the malicious program. And we use the AI model to check the hidden API code they use in those binary because those hidden API inside those highly obfuscated binary because it stands for those binary try to use some malicious sensitive API don't want to traditional antivirus to scan them. So and on the right side, you can see that as a quick demo, we have prepared out of the box tool on our GitHub. You just clone it, our project, and you can just directly use our tool right here and put a EX program file to our engine, and our engine will tell you what kind of hidden API inside this obfuscated binary. So you can just do the follow-up research. And in our large scale threat hunting, we found out two kind of evasion trick strategy is widely used by the bad guy. And first is anti-sandbox and anti-emulation still works. Those binary will try to evaluate that is under a virtual machine or under a sandbox machine, and they will try not to expose any attack behavior to against those binary be flagged as a malware binary. And another one is my favorite I will introduce is some bad guy try to use the VC.NET hybrid, use the C#.NET part of code and the assembly part of code at the same time. That will be a very challenging for the modern antivirus. Okay, so in total, for the whole month, we do the experiments and we collect around 1,200 fresh, highly obfuscated binary from the VSTotal, and we found out if you try to using the traditional Yara rule directly to scan those fresh binary, you found out those Yara rule signature-based scan can only detect around 78 different behavior, and those behavior are insensitive. For example, using the UPS packer, screenshot, or using the keylogger, those behavior are not, they are insensitive. So you just using the Yara rule can directly to scan them. But however, we found out there is more than 400 binary containing with the hidden behavior only use our AI engine can detect them. And those behavior around 18 different behavior are very sensitive. For example, this binary will try to shut down your antivirus. It will try to scan the service name. Is there any virtual machine or antivirus? Or it try to using a hidden API to using privilege escalation. Okay, so let's see two cases. It's my favorite, and the first one is a backdoor, very highly obfuscated binary try to drop a binary using a shell execute this API to drop a malicious binary and also try to position on your victim. And you can see on the right side here, our AI engine can tell this unknown API code, that is sh get spatial folder path W, this Windows API. And why? Because our AI engine can tell you, because of the API usage, if the magic number 7 and 16 put at the argument value position 3, stand for the SCSIDL startup and the CSIDL desktop dictionary. So you will know this Windows API, if used, this binary will try to drop a binary in your startup folder to position a backdoor on your victim. And you can see such a case is very difficult for the traditional detection engine because of there's no any magic number or any signature for your detection engine to do the rules again. So it's very difficult for the modern detection engine. And another case, this one is my favorite, and you can see this binary containing assembly code that is basically you can see on the screenshot that is C++ written, that is assembly part of C function inside a C#.NET part of program. So which means you can see this sample, only 2 vendors on the ViceTotal can detect them as a malicious program. And our AI engine can detect them because of our AI engine can detect this C function inside a .NET part of code. It tries to use the create process to create a suspended binary process, then inject the shellcode or P binary into this process and using the created remote thread. And however, those Windows API now you can see is invalid, is illegal, but those Windows API only be initialization by the .NET part of code. So what if your antivirus detection engine cannot at the same time to simulate the .NET part of code and also at the same time to simulate the C++ part of code? If your detection engine cannot at the same time to simulate the 2 parts of code, and you won't see the whole picture of this binary malicious behavior. Okay, I will hand over to Ian to share the further more about how we use this AI engine on the shellcode and commercial package detection.
Okay, so thanks to Sheng-Hao for providing more details on our engine and also share the first use case and also demo how it is. So now let us move on to the second use case of our engine on Windows shellcode. So first, we need to know that shellcode is usually designed to be as simple as possible. The reason for this is that the memory layout is unstable, and attackers don't want their shellcode lead to unexpected crashes, so they often design their shellcode as small pieces of code without difficult obfuscation. So with this understanding, if we can identify the symbols of those unknown pointers that used in the shellcode without running the shellcode payload, it will be easier for us to understand and general behaviors for the detection. So we use our engine to walk through each code block of the shellcode, collecting the use-defined chain to infer the unknown APIs that is used inside the shellcode, such as those highlighted in the yellow boxes in the following picture. So these 2 pictures are how shellcode looks like inside the IDA Pro, and we can see that So we can see that on the red boxes over here, it is going to parse export table to get the Internet Connect A function. And we can see under the red boxes over there, the yellow boxes of a lot of the pop instructions, it is preparing the argument values that is the Internet Connect A is going to use. So our engine just use the use-defined chain to collect these kind of arguments that function code is going to prepare, and we can identify what kind of unknown APIs it uses. So here is a practical case that when we use our method to analyze shellcode. So this sample was first seen in May 2023, and as shown at the yellow boxes, over right here, we can see that there is a Cobalt Strike shellcode payload over there. And we can observe, we used our model to delve deeper inside the shellcode payload and obtain its use-defined chain, as illustrated in the middle right of the picture. And after scanning, our method analyzed the use-defined chains on the stack and identified the parameters in their own position as shown inside the red boxes over right over here. So we can see that it is going to use some arguments inside the function code. And as we can see that apparently under the left side of the picture, as the window partial shows that it detected that there is a virtual alloc function over there. So here is our demo, and after we scan the sample with our engine, it will display the top 5 related APIs that it infers for the unknown APIs in the shellcode sample. And the priority of these top 5 APIs is from left to right, meaning the one that on the left, right are the most API that it predicted by our engine. So as we can see that our engine over there can infer that there might be a HTTP open request over there. So it can help human analysis to analyze whether it is. And right now here it finds out that there is a virtual alloc function over there. So we can double check that if it is okay. And as the other function over there is that it detected there is an internet read file function over here. So as we can see in this video that this kind of shellcode is going to do some C2 connection using the HTTP open request and then drop files to the victim's computer. So now let us move on to the last use case where we attempt to dissect the behavior of the commercial packers without unpacking those programs. So that's before delving into how our engine works, we need to first see the detection problem of modern commercial packers. So for commercial packers, it is difficult for modern antivirus or EDR solutions to extract the pure protected code for detection. So if we try to extract the protected code, original code, we usually, as human experts analyzing, using reversing engineer analyzing, we usually use these following strategies. The first step is process dumping. So this is because that even though the original program code is packed, it still needs to decompress into process memory to achieve the memory layout created by the original program's compiler. So after dumping the process, the second step is to reverse to find the original entry point of the original program. So after dumping the memory layout, we need to locate the original entry function to access the rest of the original program. So this step is essential for identifying the range of the import address fields used by the .text code. And to the final step is to rebuild the import table. So Win32 APIs are the only way for a program to interact with the kernel. So once we have rebuilt the import table for the dump memory, we can finally allow the detection engine to scan through the protected PE files. However, commercial packers put a lot of effort into making the original entry point impossible to be observed, and they will also use some router functions to redirect the import address fields. So they do not directly jump to the API addresses, making it more difficult for analyzers to rebuild the import table. And as shown in the picture right here, this is the picture that shows a pack sample that open inside IDA Pro. So on the top right of the picture, that classifies that we are inside a VM protected memory layout, while the function is linked to another memory table for API calls. So after running our engine first to analyze this sample, which is shown in the bottom right side of the picture over here, this is the result of our engine running through to the unpacked program. We found out that there is an unknown API that was inferred as a virtual alloc by our engine. So according to this, even though that it is packed, the use-defined chain method that we use to infer these unknown APIs still can effectively detect hidden APIs with our engine. And here, this one is also an interesting finding we want to share with everyone, because this program code is actually the VM Protect itself. So as shown on the above of the picture, this is an unpacked by human analyst that we can clearly see a write process memory API at the bottom over here. Yes, this is a write process memory function call over here. And at the bottom of the picture is the original code that we fed into our engine. So we can see that not only the packed original program can be detected, we can also know what kind of behaviors of VM protect these commercial packers perform to pack the program, or how they check the programming is running. So the above samples we presented are all VM protect the commercial packer, but since our method can infer the use-defined chain of the pack programs, and many packers cannot effectively obfuscate the stack, so we believe that this method should work on not only VM protect, but also on other commercial packers, such as the MIDA or also the UPX itself. So we actually also try our engine on the MIDA, and it works well too. And now this is our demo on how our engine running on the program packed by the VM Protect itself. And so we know that without dumping and finding the original entry point and the import table, we cannot determine the APIs of the program using through simple reversing. But however, as we show in the video, we can use our engine that it can scan through the program's code blocks, and it probably takes like 30 seconds to scan the entire program. And we can, based on the results from our engine, you can see that this program probably tries to use some WSA socket or create process and reduce open key over here. So yeah, we can see that there is a create process over here. And also the registry open key. So we can know that this program is going to register under the Windows current version run. And yeah, and over here is another virtual alloc that is detected by our engine. And another finding is that this one is more interesting because this is actually the packer itself. It is going to use the get module file name over here to know that whether the packer is still running or not. So after presenting the use cases, let us move on to the last part, conclusion and takeaways. So there are still some constraints and limitations to consider. The first one is the difficulty of the intent analysis on multi-threads and OLLVM. There are three common limitations, which is classic path explosion, difficult halting problem, and multi-threading problem. So the classic path explosion problem is prevented by our method because our method doesn't scan through all the branches of the code. We only scan through the relationship of the cross data. So this helps us to prevent the path explosion problem. However, for OLLVM, the performance issue to scan binary files in a limited time and recording all of the use-defined chains on a highly flattened control flow graph is a difficult halting problem to solve. Additionally, the order of the data initialization in different thread and cross-thread data passing to Windows 32 API in real-time process are classic challenges for intent analyze. And the second major constraint is the boundary coverage issue of split binaries. As mentioned in the paper, so all you ever wanted to know about 32 and 64-bit binary disassembly, the state-of-the-art community disassemblers can only cover up to 80% of the binary functions. And even for the commercial or nationally supported disassemblers that use heuristic pattern scanning, they can only cover up to 95 to 98%. So if some attackers that can build up some code that can detected by those commercial packers, we still cannot detect all the functions. And at the end of this talk, we will open source and put our tool on GitHub, hoping to empower the Blue Team community. So for takeaways, we hope that after this talk, the audience will learn strategies for using machine learning on symbolic execution for practical malware analysis against code obfuscation, and even with well-known commercial solutions. And we also hope that audience can understand the flaws of auto sandbox and AI classification detection when analyzing those VC.NET samples. So our presentation ends here, and thanks for your coming. If you have questions, feel free to ask.